So today's lecture, we will continue, try to finish delta function. There is, I think, two properties left. Then go for an example about this. Then discussing the exponential function and the LTI system. So today is the 24th, January 24th, Wednesday. So the reading today, page 35 to 40. While next lecture is Friday, the readings are page 35 also to 40. And the due date for the MATLAB projects, which is Friday. While today I assume we already, I'm sorry. We might be after this. Today should be the homework 2 deadline. Then in Monday, 29, which is the due date for the MATLAB projects. And the reading still between page 35 to 40. Then in Wednesday, 31st, the reading will be between page 40 to 50, and I think it will be the deadline for homework 3. So keep in mind to look at homework 3 and see what other problems, so please refer to Canvas and see what's more details. Now, there is, back to delta function, we used to know delta of t minus tau. That's what we do several integrals. Now the question is, how about if we have time scaling, which is if we have delta of at, constants, at. How can we deal with this? So you need to keep in mind that a, of course, will not equal to 0, because if it will be 0, it's delta of 0. Now we need to look at a. There are two cases, if it is positive or negative. So case 1, when a is larger than 0, or in other words, positive. So how can we deal with this? Let's imagine that there is the integral between negative infinity to infinity, delta of a of t dt. Now, how can we solve this integral? Because we have a of t. So we have something like change of variables that we can do in math or in calculus, I think calculus 2, in the integration. I don't know if you remember change of variables. Change of the integral variables. So, for example, I'm going to assume tau equals a of t. So, what will happen? T will be tau over a. Then, the derivative, dt equal d tau over a. Okay? So, we can, how about the terms? So, we have the integral terms. When t equal infinity, what will happen to tau? Which is infinity over a, that is going to be infinity. Because here a is positive. When t equal negative infinity, then tau will be negative infinity over a, which is going to be negative infinity. Again, here a is positive. So by changing variables, it will be remain between negative infinity to infinity. It will be delta of tau d tau over a. So we can make 1 over a, since it's constant, put this outside of the integral, then the integral between negative infinity to infinity, delta of tau d tau. And of course, this integral equal to 1, which is going to be as 1 over a times 1, so the answer will be 1 over a. So therefore, whenever there is a time scale, it will be 1 over a. Now, this is for first case when a larger than 0, which is, this is case 1. Case 2, how about if a is negative, below than 0? When a less than 0, which is negative. How can we do the integral, which is the integral between negative infinity to infinity, delta a of t dt. We will apply the change of variables. Basically, we will assume tau equal at, therefore t equal tau over a, then dt equal to d tau over a, the same thing, there's no change as the previous case, but the thing that happens by the term or the integral period, which is when t equal infinity, what will happen to tau? Tau will be I think by the terms of the integral, tau equal 80. So I'm just going to do a correction here. I apologize. Please make this correction because we know tau equal 80, so it will be a times infinity equal to infinity. Here negative a times infinity equal to negative infinity. Here the same thing, tau equal to 80, which is going to be a times infinity. Since a is negative, then negative times infinity will be minus infinity. Then when t equals negative infinity, tau will be a times negative infinity, but this is negative times negative will make it positive. So when we do the change of variables, the integral terms will be between infinity to negative infinity, delta of t, d delta of tau, d tau over a. So the thing that we have, which is, it's between infinity to negative infinity, not the opposite. Why? Again, why this thing happened? Because a is negative. So when we do the terms, negative, like what we did here, negative times positive will make it negative, and here negative times negative will make it positive. That explains why we do this. Then, in order to fix this integral, we will, as we know something like in the integral properties, we know the integration here, between a to b of any function dt equals negative b to a f of t. So what I'm going to do, I'm going to swap them here, swap this integral to be negative integral between negative infinity to infinity d tau over delta of t d tau over a. So the thing, the modification that I did in the integral, I changed the from infinity to negative infinity to make the opposite. So it will be as move a to the other side, it will be negative 1 over a. Then the integral negative infinity to infinity delta of tau d tau, and this is equal to 1. So as a result, it will be negative 1 over a times 1, which is going to be negative 1 over a. So we have two cases. The first one, 1 over a, the other one, negative 1 over a. So in summary, the integral negative infinity to infinity delta a of t dt equals to 1 over a when a larger than 0, negative 1 over a when a less than 0. That's the sum. Or we will say that since it's 1, if it is positive, it will be positive. if it is negative, the overall thing here, negative times 1 over negative, the overall will be positive, right? So as a result, we will say negative infinity to infinity delta A of t dt will equal to 1 over the absolute value of A. So it will be positive anyway, because if it is negative, it will affect the integral terms, then the overall results, this is the first result or the first property, which is when we have a time scale, it will be, the integral will not be 1 over the constant here, the absolute value of that constant. The second observation that we can do, which is whenever we have delta A of t, it will be as 1 over the absolute value of A times delta. Okay? Is this clear? So whenever we have any constants, 1 over the constant, the absolute value of that constant. So we can get rid of the time scale. So we can make the problem much easier by removing this time scale, time constant. Then now also let's assume A equal negative 1. So what will happen? Delta of negative t equals 1 over the absolute value of negative 1 delta of t. So as a result, delta of negative t equals to delta of t. This is a third rule that you need to know. So we can realize that delta of negative t equal the same as delta of t. And what's the meaning of this? Does this mean delta of t is even symmetric or odd symmetric?
Even.
It's even. Actually, even symmetric means x of negative t equal x of t, while odd means x of negative t equal negative x of t. So as a result, delta of t is an even symmetry. Okay? Because delta of t equal to negative delta of negative t. Is this clear? So these three properties are important for delta of t and the integral of delta of t. Let's give you an example, like delta of for example 3t will be delta of t divided by 3. That's it. When I say delta of negative 5t will be delta of t over 5. So whenever I have a constant times the time, I can remove it easily. Okay, does this make sense? Now let's go to an example. Important example. Focus on this. Given f of t as shown. This is f of t, here's the time t, time 2, this is 1, negative 2, here is negative 2. Okay? So we have this function, this signal. So let's do the following evaluation. Evaluate the following. some part of the evaluation can be like find the function kind in terms of step function. We can do it easy. So the turn on at negative t, turn off, or there is a change at t equals 0, and turn off at t equals 2. So you can try it at home. Like I'm not going to write it now, but I would like you to do it, which is write the function as unit step. So you will do it for yourself. If you have any difficulties, please feel free to reach me and I can help you. Now, the other parts, which is I need you to calculate the integral between negative infinity to infinity f of t delta t minus 1 dt. How to calculate this? So the first thing is get rid of delta, then you can do the integral. So try to remove delta. Now we have the integral of delta according to the properties that we know about delta function. Or by the way, delta function is called, in other words, impulse function. Delta, sometimes we can call it as impulse function. Okay. Now, how can I do the calculation? According to the properties, it is shifted here, t minus 1 equals 0, so t equal 1. Therefore, the answer will be f of 1. That's it. Then go to the function here, locate where is 1. 1 is located here, so f of 1 equal to 1. Right? That's simple. So even I didn't do the integral, it just like apply the delta properties. Now, number 3. Calculate the integral between negative infinity to infinity f of t delta 2t minus 4 dt. I can apply the properties of delta, but I have a challenge here. What's my challenge? Which is I have 2t. Okay, how can I deal with this? Basically, we can simplify it by taking 2 as a common factor, which is, here's the integral between negative infinity to infinity, f of t, delta, take 2 as a common factor will be 2 minus 4 over 2 dt. Okay? Just take 2 as a factor. Then, we can simplify it more like negative infinity to infinity f of t delta 2 t minus 2 dt. Now this is as factor a, this is as factor t, so we'll take the absolute value of a. So basically, according to the formula like delta of at equals to delta of t over a, then it will be as the integral negative infinity to infinity f of t, then delta t minus 2 over a, which is 2 dt. Okay? Does this make sense? Now, put the half or 1 over 2 outside of the integral, negative infinity to infinity, f of t delta t minus 2 dt. Now, t minus 2 equals 0, therefore t equals 2. So according to the properties, it will be 1/2 f of 2. Okay? Let's see here. Yes. Now, let's go to f of 2. Here is 2. F of 2 equal to 1. Is this right? F of 2 equal to 1. Therefore, it will be here 1/2 equals to 1/2 times 1 So the answer will be 1/2. Okay? Yes?
I have a question. So when you read a unit function, you take the value to the left of the number, like when it drops down. But at the 2, do you read the value to the left of the number, or do you take the maximum value?
Yeah, basically we will take this value. Take the maximum, which is each given here. Yes. Here we will take like the maximum.
You take the maximum?
Yeah, take the maximum. Okay. Now, any question about number 3? Okay, let's go to number 4. The integral between -1 to 2 f of 1 minus t delta 2t minus 3 dt. Now it's getting more complicated. So the first observation, try to look at delta. So we have 2 here. We will take 2 as a common factor. So we will do as -1 to 2 f of 1 minus t delta, take 2 as a factor, so it will be 2 minus 1/2, 3/2 1/2 dt. Now this is a, this is t, we will make 1/a, so the integral according to the properties, -1/2 f of 1 minus t delta t minus 1/2 divided by a, which is 2, dt. Puts 1/2 or 1/2 outside of the integral, so it will be between -1 to 2 f of 1 minus t delta of t minus 1.5 dt. Now I'm ready to use the integral, which is here t minus 1.5 equal to 0, therefore t equal 1.5. Now the concern is we cannot say directly it is f of, for example, 1 minus 1.5. We cannot say that. We need to check the limits. Look at the limits here, -1, 2, and we have 1.5. So the question is 1.5 between -1 to 2? Yes. Then I'm ready. Yes, I can do 1/2, then f of 1 minus t, which is 1.5. That's how. So 1 minus 1.5, it will be 1/2 f of -1/2. Then what's f of -1/2? Go to here, so 1/2, -1/2, almost located here. So it will be 2. So it will be here 1/2 times f of -1/2, which is 2. So 1/2 times 2 will be 1, and that's it. Okay? Is this clear? So basically, here we are trying to play first inside the delta, do the integral, then find the function. So that's why this example is convoluted, including many things in our delta. Let's do this integral between -1 to 1. F of t minus 1 delta 2t minus 4. So the first thing, we have 2. So we will take 2 as a factor. So integral between -1 to 1, f of t minus 1, then delta of 2, between brackets 2 minus 4/2, which is 2, dt. Then we will put 2 outside, this is a, this is t, we will put 2, 1/2. Integral between -1 to 1, f of t minus 1, delta of t minus 2, divided by 2, dt. Put 1/2 outside of the integral between -1 to 1, f of t minus 1, then delta t minus 2 dt. So now look at t minus 2 equal to 0, therefore t equal to, I cannot say direct 1/2 f of 2 minus 1. Why I cannot say that? Because I need to check the integral limits. So the question is 2 between -1 to 1? No. Therefore, saying 1/2 f of 2 minus 1 is incorrect. So the answer 1/2 times 0 will be 0. Okay? Because it's outside. I'm doing the integral where there is no function. I'm doing the area of nothing, which is 0. Okay? Any question about these 5 examples? We'll give a few seconds to write, then we will start the exponential. So exponentials. So the exponential, as we know, it's e, the exponential function. But here it's depending on is it power of positive or power of negative. For example, when we have e power t over tau, tau is time constant. While 1 over tau related to the decaying rates. The higher number, 1 over tau, the faster decay rate, or the slower time constants, the faster, right? Because 1 over the time will be like speed, or distance over time will speed. So when we have the exponential, here is first scenario. E power t over tau. That's how the exponential is growing. Such that at t equal infinity will be negative infinity equal to 0. The exponential equal to 0. While at t equal infinity, the exponential will be infinity. And at t equals 0, it will be 1. Because exponential of 0 will be 1. Anything power 0 will be 1, right? So it is centered at 1. Or, I mean, actually, like, that's our target at 1. Or, I would say, like, the centered at 1. Or the origin at 1. How about if we have e power negative t over tau? Will be very similar to this, but it just mirrored. It will be like this. So here is 1, then here, for example, at t equal negative infinity, exponential will be infinity, while at t equal infinity, exponential will be 0, and here at t equals 0, it will be 1. So all of these cases, it will be 1, no matter if it's positive or negative. And we know all of this from math, so there is nothing new. Just like we make sure that t is the time constant, 1 over t is the decaying rate, so the larger decaying rate is the constant system. So if, for example, you have e power negative 2t, or when we have e power negative 5t, it will be faster. We'll check that. Something like that. So basically, it will be faster when we have larger amount of decaying rates. Now, how about most likely exponential? It simulates some practical applications like the batteries. Sometimes the batteries can be charged or discharged as exponential. Also in circuit analysis, you've learned exponential a lot. So another thing about the exponential, if we have a shift. So let me call this is 1, this is 2, now 3. When we have f of t equals e power negative t minus to divided by tau. How we can, how is this function will be plotted? Actually, it is still, since it's negative, it will go down like this. But the thing is, it will not be centered at 0, it will be centered t minus tau equals 0, so t equal to. So here the center. And I mean the center, which is, here it is to. This means it will be 1 only at to, not at origin. While in the previous thing, t centered at t equals 0. Okay? So basically, we're just trying to define the center. So when we have a time shift, just shift the center. If you are shifting right or left, depending on what's inside it. So t minus tau equal minus to equal to 0, then we can define where is the center point. Now, other thing here, when we have f of t equal e power t over tau times u of t. Okay, how can I plot this? We know e power t over tau, this means it is increasing with time. And since u of t, it will start from t equals 0. So here is t equals 0. Otherwise, before t equals 0, everything is 0. Then here, since it's centered at 1, it starts from 1, then increases. So that's how it looks like. Okay? Number 5, f of t e power negative t over tau u of t. Again, here is the time plot. Here is 0, since it's unit step, it starts from t equals 0. Then, before t equals 0, everything is 0. Then at that, it will, since it's centered at 1, it is centered at 1. Then what else? Which is, it will be decaying, not increasing, because decay with time, since it's exponential. Exponential with negative sign. Okay? Yes?
So for the third example where you shifted t a row, you're saying that the center at there is going to be 1 on the y-axis?
Yeah. Which is the center, the location of 1 will be at 0. So here I mean by the center, which is where's the location of 1. Now number 6, half of t equals e power negative t, or actually between brackets, e power negative t minus to divided by tau u of t minus t. How can I plot this? So the first thing, it will be enabled at TO. So here is TO. Before TO, everything is 0. At TO, it will be changed. The other thing, which is, so t equal to 0. The other thing, the center, t equal to 0. Here is the center. Therefore, at TO, it will be 1. center located means the location of 1. So if we start from 1, and since it is negative, it is decaying. So look like this. So when we have TO here, it just shifted a little bit. Okay? And also, here now something related to the integral from 0 to infinity e power negative t dt. We know the integral of the exponential, it is easy, which is 1 over negative 1, integral of t between 0 to infinity, which means it is negative 1 times e power negative infinity minus e power negative 0, which is going to be, in other words, by flipping the sign, e power 0 minus e power negative infinity. Then it's going to be 1, e power negative infinity means 0, equal to 1. So you know this also from mathematics. So that's the exponential with time domain, or it just as a real number. Now we will make it more complicated, which is complex exponential. You can refer to appendix B in the textbook for the complex exponential. Now, let's recall in calculus 2 the polar form and the rectangular form, and also in circuits analysis. We already discussed the polar form. So, e power j theta. Do you know the Euler formula, Euler equation, which is e power j theta equal cosine theta plus j sine theta. This is called Euler equation. This is very famous and very important in electrical engineering, not only in this course. You will use it later in control system as well. You will use it in the DSP, the other part of so Euler formula is something very important that every electrical engineer must be familiar with this. And J, as we know, the square root of negative 1. Okay, so that Euler formula, Euler equation, basically this is very similar to say, this is rectangular coordination, this is like polar coordination. But polar coordination means to write R, then we write R, something like that. Well, there is no, I'm going to assume R can be as a factor. And sometimes we used to say it's x plus jy, something like that. Also, whatever. Just let's focus on the Euler formula itself. So, let's look at the axis. This is the real axis, this is the imaginary axis. So when I say e power j theta, here's a vector. So e power j theta. So here is the angle theta, and since there is no constants, the absolute value e power j theta alone equal to 1. So the magnitude here is 1. I put this is 1. Then in order to convert this or to make the projection for this one on x-axis and y-axis, since we have theta, make the projection, this will make it cosine theta, and this will, the other side will make it sine theta. Just make the projection, one cosine theta, one sine theta. And as we know as well from the math, since it has 1, and if theta is changing, this will make as a circle. They're changing with theta under constant or units. It's called constant magnitude. So I'm going to assume the magnitude is 1, so the radius will be 1. So as a result, this point is 1, this point is negative 1, this point is j, this point is negative j. So again, in Euler formula here, we have e power j theta. When theta equals 0, this will yield e power j0, which is equal to 1. Then, when theta equal pi over 2, or in other words 90 degrees, this means e power j pi over 2 equals to j. You can verify this by doing Euler formula. Sine theta, cosine theta plus j sine theta. When we have theta equal to pi, or in other words 180 degrees, e power j pi equals to negative 1. Keep in mind, every time when we do e power j theta, theta must be in radian. We cannot do it in degrees. That's according to polar representation. Then when we have theta equal 2 pi over, or 3 pi over 2, which is 270 degrees, e power j 2 pi, or 3 pi over 2, equals to negative j. When we have theta equal 2 pi, this is equivalent to 360 degrees, or in other words, this is the same as 0, or 0 angle, e power j 2 pi, which is equal to 1. Because recall, at 2 pi or 360 degrees, you are starting with the second line, second cycle. We know, as a circle, 360 degrees. When you reach exactly 360 degrees, this means you are starting with the second circle, which means 360 minus 360, 0. Okay? Or in other words, 2 pi. Now let's keep going about the exponential. How is the format of the exponential will be when we have a complex, assuming there's an amplitude. So x of t equals a e power j omega t plus theta. And I think you're familiar with this from physics, from circuits. So omega is the frequency, theta is the phase shift, right? So in order to do this in Euler formula, it is a cosine omega t plus theta plus j a sine omega t plus theta. Then if we plot the imaginary axis, the real axis, so this is, for example, the arrow here, then this is the angle omega t plus theta, then we have that circle that's changed with the amplitude is changed. Since the amplitude is 1, so this will be JA, this will be A, this will be negative JA, this will be negative A. Now how to find these points? So make the projection on the x-axis, the projection on the y-axis, or in real time or imaginary time. So here is like real, this is imaginary. So in real time, it will be, make the projection, a cosine omega t plus theta. In imaginary axis, it will be a sine omega t plus theta. And there is a j, just to distinguish this j. Okay? So as a result, what we used to do before, when we do the circuit analysis, especially in phasor domain, we used to look at the real parts of e power j omega t plus theta, which is, this means a cosine omega t plus theta, something like that. Then we did this conversion. When we convert between pole or phasor to time domain, we used to take only the real parts, something like that. Now, let's go a little bit about some exponential plots. Just like we'd like to see some demonstration on how to plot the exponential using MATLAB, then do some observations. This is an example of exponential plots. So we want to plot 100 exponential of negative 2t. So keep in mind, we did the step size is 0.1. If you want it more accurate, reduce the step size as much as possible. Then we make the range between 0 to 100. So the output looks like this. So we can barely see what's going on. So we cannot see what's going on here. Okay, so we need to do some modifications. So the modifications can be done on the range. So in order to get a clear image, we can reduce the time. Don't split from 0 to 100. How about displaying from 0 to 10 seconds? So you can get a clear image. That's one thing. Other thing, like how about if we need to plot x of t equal 100 equal negative 2t times ut. So the thing which is the difference between this one and this one is the addition of u of t. How can I do this? In case if you need to do it, you will just modify on this code by adding times u of t 0, and don't forget to write the dots. Dot means elements, dots, and plot means element by element. U of t, comma 0, this means you need to already define your own function as u of t. I think we already discussed how to define u of t, t0, I already told you to do it. So I'm assuming now you already defined that function, and you already store it. Now you can use it. Because again, there is no function in MATLAB called u of t, t0, or t0, but you need to define it by yourself. Then, u of t, t0, just multiply. That's how we, in case if we need to u of t. So the modification that we did here, let's forget about u of t, just in this explanation. So in order to make it more clear image, so the first thing is we make between 0 to 10, and we change the line width to be thicker, so we can see a good image. Then, this is still sometimes someone can say, how about I want to make more zoom? I mean, because sometimes it's showing only the sparks, might not be good, so how about if I want to show it from 0 to 5? So basically, you can change the time to be 0 to 5, then we can get a good image. That's how the way that you will do when you are plotting your graphs. Don't just like make it randomly. That's the graph that I got and that's it. No, try to simplify so it can be readable. Then you make it like this one. Also, the x-axis or y-axis, you can actually modify it by making some changes. So one of the things, don't forget to label. So you can have a professional and make the title. So you can have a professional plots. So your homeworks, don't just like do the plot like this and get any plots. Or don't like make the plots even like this one. This one, yes, it's correct, but it's not professional. To make it professional, you need to label x-axis, label y-axis, make the title, like what we have here. X-axis is labeled, y-axis is labeled, the title is written, and also, I encourage you to make a grid on, so we can have these guidelines. If the grid is not on, you will have like white. But here, it will be like this. So, this figure looks more professional than the whole one, even though like this answer is correct, this answer is correct, but this one is not professional, the other one is professional. That's why I said during the homeworks, there will be 2 points on neatness of the solution. Make sure your solution is good. Now, also, just here for demonstration, it's not necessary to do it, which is sometimes you can do the log. If there is a lot of big changes, you can do similar on this one. That's just as a demonstration. Okay, so next lecture I'm going to continue more in exponential signals, then we will start the LTI system. Yes. Any question? By the way, I think we have published these notes in Canvas.